Hi, everybody. This is Pano Santos. Let me give you a brief outline of what we are going to cover today. So I will be presenting challenges and trends in the telecom industry. Then Professor Haitao will discuss the technician routing and scheduling problem and give a high-level view of the model formulation. Then I will be presenting a problem instance, essentially providing data that later on we will use in the demo. And then I will give what we call the business value proposition, why this type of technology is important for the telecom industry. Then Dan and I, we are going to give a demo, and then we will have plenty of time for questions and answers. Next slide, please. So the telecom industry is facing many challenges, and to respond to these challenges, and they are following many trends. But one of the trends that is key to respond to the challenges that the telecom industry is facing is artificial intelligence. And one approach very important in artificial intelligence is mathematical optimization. Why mathematical optimization is very important? Because with mathematical optimization, you can maximize the operational efficiency of your organization, consider business constraints, business rules, multiple objectives, trade-offs between objectives. So mathematical optimization is a very important tool for maximizing operational efficiency. Next slide. And in particular, we have identified several problems at the strategic, operational, and tactical level that can be addressed with mathematical optimization. One particular problem, which is very important for the telecom industry and in general for any service industry, is workforce planning and management. Why? Because labor resources are critical for the delivery of services, and at the same time, labor resources are the most costly. One particular sub-problem of workforce planning is precisely this telecom technician routing and scheduling problem. So before Professor Haitao will explain the details of the model, let me address a little bit about the complexity of this problem. Next slide. So the technician routing and scheduling problem can be formulated as a class of problems in operation research that are called vehicle routing problem. And one particular instance or one particular case of vehicle routing problem is the so-called traveling salesman problem. This problem is one of the most important combinatorial problems in the field, and it's an instance of a vehicle routing problem. And to describe the traveling salesman problem is very simple. Suppose that you have a salesman that needs to visit a number of cities, and he wants to find the shortest route that goes to each city once and returns to the origin city. So it's very easy to describe, but this problem is very challenging. Next slide. So suppose that you have a traveling salesman problem with 100 cities. And the number of possible routes for this salesman will be 100 factorial. 100 factorial is a number with 157 digits. So this number is really immense. It's really very difficult to conceive. Why? Think about the number of atoms that exist in the known universe. This is a number with 80 digits. So the number of routes with this relatively simple traveling salesman problem with 100 cities has almost twice the number of digits of the number of atoms in the universe. So even with the fastest supercomputer that can make 200 petaflops per second calculations, it will take an astronomical number of years to enumerate all the possible routes to determine the optimal one. So you need beyond the computer power, you need very sophisticated algorithms to solve this instance of the vehicle routing problem that is the traveling salesman problem. Because the vehicle routing problem that we are going to address is even more difficult. Next slide. Why the vehicle routing problem that we will discuss is more difficult than the traveling salesman problem that we just described? Because instead of having one salesman, we will have several salesmen. Also, each salesman will have a limit time to do the tour, and each salesman will be qualified to visit only a subset of cities. And for each city, there will be a time interval to visit that city. That's the type of routing and scheduling problem that Haitao is going to describe now. So I want to spend this time just addressing that this is a very, very, very complicated problem, and it's very important for the telecom industry. So I think I will stop with that, and I will let Professor Haitao to continue describing the problem and the model. Haitao, take it from here, please.
Thanks, Pano. Let me start with some motivation about this application. This application was really motivated by the operational challenges and decision needs at a small to medium-sized telecommunication company. Through our conversation and communication with domain experts, we understand the company is typically facing the challenge of meeting customer satisfaction. Specifically, those means, for example, how to minimize customers' waiting time, to quote them with the time window which the company can actually realize, and also making sure that the service level agreement is satisfied, and certainly deliver the service with quality within the time window is a huge challenge and an important performance metric. And the company is also facing the decision needs and challenges to optimize the use of their available resources. In this case, it's the skilled, multi-skilled technicians. So the company needs to assign technicians with the right skills to the right job at the right time and the right location. Although we present our application in the setting of telecommunication industry, we believe our model, with proper adaptation and modification, it can be well applied to a number of other application settings. For example, in transportation, a prominent application is to optimize the transportation operation for goods and people. And each application has their unique features. In the transportation industry, for example, companies or 3PL often need to address the so-called pickup and delivery feature of the operation, and sometimes backhaul, minimize the cost of backhaul and how to utilize the backhaul capacity. In a bus operation setting, we may address the bus tabling or rostering application as well. Very interesting applications for food distribution and delivery. So the unique feature there is during the food transportation, often the company needs to address the cold chain requirements due to the perishability feature of many of the type of food products like vegetables and fresh meat, for example. So that's very unique feature we need to address there. In healthcare, there are many applications that address home care scheduling, routing, and vaccine delivery, and where the preference of timing matters a lot. And again, sometimes the drug also has perishability issue, which require the cold chain consideration. Such routing and scheduling application also has lots of opportunities in emergency logistics or the so-called disaster relief logistics, humanitarian logistics field, to distribute and deliver the emergency supply for disaster relief. There again, we should consider the limited capacity of supply, the timing of delivery, and the priority of the regions to be covered. Another potential application industry related to our example here is the utility industry, where it has the decision needs that is very similar to what we're presenting you today. So for their technician service dispatching and scheduling problem, where the companies may also consider the priority of orders and customer time window to be satisfied.
Thank you, Haitao. So what I'm going to do is to describe the problem instance that we call the base scenario. So in this particular scenario, we consider that we have 7 technicians. And in this first table, we include the capacity of each technician in minutes and the base depot that each technicians belong to. So for example, Albert has a capacity of 480 minutes, which is the equivalent of 8 hours of work. And his base is in Heidelberg, and similar information for the rest of the technician. The next table describes the type of jobs that each of the technicians can perform if they are qualified for the job, meaning that they have the skill. Also, we have the priority and the duration of the job. So for example, for equipment installation, the priority is 2 and the duration of this job is 60 minutes. And the largest the priority means that this is more important because we are going to use this priority as weight in the penalty function that we minimize when we are solving this problem. So highest priority is 4, lowest priority is 1. Next slide. In this first table, we have the customer's location and job requirements. So for example, take customer 3. Customer 3 is located in Baden-Baden. The job that this person requires is a repair regular job. This person has established that the job must be completed at 11 o'clock in the morning. And the time window given to start the job is between 8 o'clock and 10 o'clock. And this time window to start the job considers that the job takes an hour to finish. So in this time window, the latest that this job will be completed is at 11 o'clock. It's important to mention that the time horizon for this problem is between 7 o'clock in the morning and 5 o'clock in the evening. So it's 10 hours. And everything is expressed in minutes, in relative minutes respect to 0, which is 7 o'clock in the morning. And the last table basically tells us the travel times between different locations. Locations can be depot to customer location or customer location to customer location. And all of this is in minutes. Next slide. So Haitao present a formulation with an objective related to minimize penalties related to customer satisfaction. So essentially, we want to make sure that the service delivery is within the time established by the customer. So we don't want to be late. So that's one type of penalty. Also, we want that the technicians arrive within the time window. So we have penalties if we need to adjust the time window to do the service. And we have very high penalties when we cannot complete the job. But another objective that we can consider is if we know the cost of assigning a technician to satisfy a customer request, and also if we know the penalty cost of completing the job late, and if in addition we know the revenues associated with the customer service, then we can maximize the total gross profit related to the servicing each of the customers. Another way to address this problem, it could be that we use multi-objective optimization or hierarchical lexicographic method for optimization, where the primary objective can be maximize customer satisfaction as expressed by Haitao, but at a secondary objective, we can maximize the technician utilization. So these are possible extensions that we can have for this. And there are many others that can be done. So why this type of approach is very valuable? With one of the key aspects of math programming is the flexibility, is the capability of doing what-if analysis, and also the flexibility that you have with math programming, that you have new business conditions, you can easily create new decision variables and constraints without the need of changing the underlying algorithm that solves the problem. So here, in this particular case, the what-if analysis capabilities allows to improve customer satisfaction by allowing customers to define service due time and reduce time windows to start the job. So dispatchers might say, okay, at this point we are using 2-hour time window, and let's see if we can reduce that time window for 1 hour and a half, and see if we have the capacity to do that. Another thing that the what-if analysis allow you is you might to react to uncertain events. For example, what happens if a technician calls sick? Then you will like to see if other technicians can fill the customer needs that you have for other customers that are not going to be able to satisfy the. So you won't have the technician to satisfy the job. Another what-if analysis that you can do. What happens if we have an extraordinary customer request and we want to fill that as soon as possible? So you can create several scenarios and really analyze and create a kind of robust schedule for the following day that satisfy customer needs as best as possible. Next slide, please. So what we are going to do now, we have a demo that we have created. So we will start with the demo, and Dan is going to show that. And in a way, Dan and his team has been able to create very nice visualization for this particular application of optimization. So here the situation is that you just have one technician, and this technician has 600 minutes of capacity, meaning 10 hours. And Dan is going to show the results of this demo, which in this particular case is closer to a travel salesman problem because you have one technician, and he will show the route. Dan, do you want to take it from here?
Okay. First, let's look at the data. I want to find the data set for this. It's called, we're calling it scenario 7. And we have the important part is the technician availability. And so, as Pano pointed out, this technician named Gina has a capacity of 600, and we've deliberately set the others to 0 because it makes an interesting test of the model. We also have, as he's shown in previous slides, the data that will be used by this model. It's currently contained in an Excel spreadsheet, but of course it could be in a database or in a file, anywhere that's convenient for the application. So let's see it running. Let's see, here we go. In fact, I've already run this one, but the way the interface works, we've got it set up to that you can browse different scenarios in the form of different spreadsheets, and then they're rendered on the screen. So we have the customer assignments in this case are all assigned to Gina. One customer couldn't be accommodated in this case, so that Slack variable that Pano mentioned previously is making it possible for the solver to find a feasible solution with this kind of crazy arrangement that we have with only one technician. And at the bottom, we've plotted out the route for Gina, since she's the only one working, going from Heidelberg, that's her hub, to Mannheim and so on through and back to Heidelberg. The objective value of this solution turned out to be, well, you can see it on the screen, but what's more interesting, I think, is the map. We've got a map rendering of Gina's route. Since there's only one, I'll make this, I'll zoom in a bit for you. So we can see that Heidelberg is the headquarters. She's going first to customer 1 in Mannheim, and so on. So we can see her route. We can zoom in and play with this any way we see fit. It makes a nice visual indicator of the kind of solution you have. So Pano, did you want to show more on this?
Yes, I will explain a couple of more scenarios. So if you switch to slide 25. Next, yes. So Dan and his team created nice visualization of the results, but let me go into more detail of the type of results that we get for the problem. With the base scenario, we created a situation that we knew the answer. This is very important when you are modeling to debug the model and to make sure that you have the right data and all of that. You need to have a realistic problem, but also you need to know the answer somehow. So basically, the way that we created this base scenario was to have plenty of capacity and capability. So you have plenty of technicians, plenty of hours for work, and also you have all kinds of capability. So with the technicians that you have, you cover all the skills that are required by the customers. So in this particular case, basically the optimal solution is you don't pay any penalties. Basically, you can satisfy everything. You can satisfy all the jobs, and you don't need to make any corrections. So the optimal objective function is 0. And the next report basically tells you for each customer which technician has been assigned. For example, customer 1 got Albert, the customer 2 also got Albert, customer 3 Gina, etc. So you know which technician is satisfying each customer, and then you have the location of the customer and the start time of the job at each customer location. The next report basically is this report basically gives you the detail of the routes that Dan was showing. So, for example, Albert, the base of Albert is Heidelberg, and he will drive from Heidelberg to Mannheim, which is the customer location, and it will be he will be driving 24 minutes. And then he will start the job precisely when he arrived to the customer location. So he will start the job at minute 24. This job takes 30 minutes. And then when he finishes the job, he will drive to Karlsruhe. And he will drive for 53 minutes. And he will start the job at minute 150. See why he's waiting there? Because the customer has the time window of the customer. He will be early if he arrives early, so we don't want to violate that. So he needs to wait some time until the customer is available to bring him to the location, and then the processing time. And then when Albert finished the job, he will go back to Heidelberg, and he will be driving in 50 minutes. So for each technician, you will have a route, and the technicians that are not used, basically they don't have a route. For example, Bob was not used, or Ed was not used, so they don't have any route. And the last table is the technician's utilization. And as you see, the utilization of the technician is very low, as expected, because that's the way that we create the problem. So let's discuss another scenario which really force the model to make more interesting decisions. In this what we call scenario 1, basically we are saying, okay, let's stretch the situation. Let's assume that the technicians only have half of their capacity, And let's suppose that customer 5 has an emergency, and customer 5 requires service first time in the morning. First time in the morning is 7 o'clock, which is at 0 minutes. So let's solve this problem with half of the capacity of the technicians and the customers that has an emergency request. So the first report tells us that there is one customer that cannot be filled with this capacity, and this is customer 4. But if you check the priority of equipment installation, that's a low priority. So the model has made the right decision, that has decided not to satisfy a job of a low priority customer. And then we see that floor can satisfy the needs of customer 5, and the earliest time that she can arrive to the customer is at minute 45, and this job takes 60 minutes. So this the system is telling us is going to be 105 minutes late. What happened is we have requested as early as possible. So this is the earliest time that a technician can get to the customer and fill the customer needs. Let's discuss another scenario that again is a little bit crazy, but just to show you how the model reacts to the different situations. In this particular scenario, again, we assume half of the capacity, and we are assuming that everybody requests their service at 8 o'clock in the morning. So again, we are stressing the system. And in this particular case, there is only one customer that we can satisfy without any penalty. This is customer 1 in Mayhem, and the job will start there at minute 24. But for the rest of the customers, the model start making corrections. For example, for customer 2, the service is going to be 20 minutes late, and also the time window of the starting the job will be 20 minutes. So for the rest of the customers, you see how the model is making corrections in terms of how late it will be, and also the making corrections related to the time windows. Next slide, please, Dan. So in summary, in these situations where for some uncertain reason we know that we are not going to be able to satisfy customer demand as we will, planners and dispatcher can take actions. So they might see, okay, can we hire a temp and to fill the job? Or at least if there is nothing else that can be done, at least they can send a text message to the customers that they are going to be affected and say, hey, for some emergency reason, we cannot satisfy your needs as requested, but we will be able to satisfy it at this time. So you are reducing the situation for the customer that the job was not satisfied as the customer requested, but at least you are telling the customer, hey, we are going to making these corrections and we will fill it in this way. So at this point, that's all that we want to discuss about the tool and demo that we have developed.
Okay, thank you.